Good evening and welcome to all of you. We have all gathered here for the distinguished lecture by Professor Ramamurty today. May I request our Vice Chancellor Sir to accompany Professor Ramamurty Sir onto the dais. I request Dean Chemistry Professor Ashwini Nangia also. Sir, please come onto the dais. And Director IOE Professor Ghanshyam Krishna onto the dais. Now I hand over the proceedings to our Dean, Dr. Ashwini Nangia. Thank you.
Thank you and good afternoon to everyone. Honorable Vice Chancellor Professor B.J. Rao, Professor Ramamurty from visiting IOE Chair Professor from NTU Singapore, Professor Ghanshyam Krishna, Director IOE, deans, heads, faculty colleagues, students from across the university. It is pleasant to see several colleagues and also students from many departments here, and thank you everyone to join us this afternoon. Professor Ramamurty was at the IASc for several years before he moved to NTU 2 years ago, and he has several collaborations with many of us who are in this room today, so it was only natural that we formalized his presence here on Hyderabad University campus through the IOE Chair Professor program, and he is actually the first IOE Chair Professor to visit our university, and so I think a round of applause is in order, and thank you very much. He travels extensively, and therefore finding a slot in the short time that we had after the announcement was made was not easy, but we are glad that you found the time. He's spending about 3 weeks in this month, and then he says he will come again sometime in the second half of January, and we will share the dates once that is known, so that any discussions that happen now can also continue on to the next month and also thereafter, depending on how the interactions and collaborations move on. So I will not take much time. We are running behind schedule, and thank you to Honorable Vice Chancellor and the IOE program for sponsoring this visit of Professor Ramamurty to Hyderabad University campus in the School of Chemistry. Thank you very much.
I'll now request our IOE Director to introduce the speaker.
Good afternoon, everyone. Welcome to this distinguished lecture. Before I introduce Professor Ramamurty, just want to say a couple of words about the IOE Chair Processor initiative, which was launched recently. The aim of this program is essentially to invite distinguished, eminent academics, researchers, industry professionals who are currently working abroad outside India, and their presence on campus not only internationalizes the university, but it sort of gives a global perspective on what is going on in current areas of research. So the aim is also that the IOE Chair Professor will mentor the academic units, faculty members, and students, and hopefully we will be able to, as Professor Nangia was saying, create a network, a global network in areas that they specialize in, and help us to move forward in this direction. So internationalization is one of the main objectives, and of course people of eminence are always welcome. And I think we are very happy that this scheme has actually attracted attention, and there are many people who will come hopefully in the near future. And I urge all academic units who are present here to nominate persons for this program so that we can actually enhance the profile of the university internationally. Having said this, it's a pleasure and both a pleasure and privilege to introduce the first IOE Chair Professor, Professor Upadrasta Ramamurty, who has kindly accepted our invitation to be IOE Chair Professor. So thank you, Professor Ramamurty, for accepting our invitation. I'll briefly introduce him. His CV is very long, and he has kind of forewarned me that the introduction should not be longer than the speech, so I'll try and keep it short. So Professor Ramamurty did his BTech B and from Andhra University, and then he went on to Indian Institute of Science to do an ME in metallurgy, both degrees in metallurgy. Then he got a PhD from Brown University, and thereafter he went to University of California, Santa Barbara, and MIT for postdoctoral stints. And after that he joined NTU initially for a few years, and from there he came back to India to join Indian Institute of Science, where he was a professor till 2018, and then he went back to NTU. Singapore seems to have some attraction for him. So in NTU he is currently the President's Chair Professor in Mechanical and Aerospace Engineering and Material Science and Engineering. For those of you who don't know NTU is Nanyang Technology University. It is ranked in various ranking profiles in the top 100, in some it is in the top 50. I think in material science and nano science is in the top 10 of the world. So it is, and I've been there, and it's a fantastic university. And he directs the structural metals and alloys program, which is a $25 million Singapore dollar nationwide project funded by A-Star Singapore. And a unique feature, in the perspective of the University of Hyderabad, is a lot of his research is funded by the industry. And this is something that I think many of us who are doing engineering and technology must learn from. I hope he tells us how he succeeds in doing this. He has published over 300 papers. He has more than 21,000 citations and a current H index of 75. He's an editor of the ActaMet and ScriptaMet, which are the premier journals for metallurgy and material science. He's a fellow of the Indian National Science Academy, the Indian National Academy of Engineering, Indian Academy of Science. He's also a fellow of the Third World Academy of Science. He's a recipient of the Scopus Young Scientist Award, Shanti Swarup Bhatnagar Award, J.C. Bose National Fellow. I can go on, but I will. He has also delivered the C.N.R. Rao Prize Lecture in Advanced Materials of the MRSI. He's been a visiting fellow in various universities across the world, as Professor Nangia was saying. And his research interests include deformation and fracture behavior of amorphous and crystalline alloys, additive manufacturing, and the development of the nanoindentation technique, which I personally know he has done a lot, very seminal work he has done. So I think clearly there is an overlap between Professor Ramamurty's research interests and the faculty members and the academic units of this university. So I think we should, in some way, hopefully go forward and take this opportunity to make use of Professor Ramamurty's presence here. So it is truly an honor that somebody of Professor Ramamurty's eminence has accepted our invitation, and he is now the first IOE Chair Professor. So I thank you again. and I invite you to deliver your lecture on structure, mechanical properties, correlations in molecular crystals. I'm sorry. But some of this work, as I know, has a very strong University of Hyderabad connection. So thank you again, and we look forward to listening to you.
May I request our Vice Chancellor, sir, to say a few words?
Professor Upadrasta Ramamurty garu. Special welcome to the University of Hyderabad as first IOE Chair Professor. Firstly, I really love that word, Upadrasta. It's a beautiful word, very profound word also. So, thank you for accepting our invitation, and thank you for spending time in the campus and interacting with our members and nourishing the system. And I hope we keep doing this recurrently. Firstly, your choice as the IOE Chair Professor is probably one of the best choices we have made, because you are at an intersection of physics, chemistry, and CEST in our university. Probably to some extent even CASEST, if I stretch it. So you're really at the real intersection point, and therefore you are our best choice, and I hope all these units will get benefited by your presence and your scholarly work. So some of us have seen your work and have been immensely impressed by the way you have charted your journey in the material science world, looking at many, many interesting correlates and trying to discover deep insights. So today's topic, of course, is structure, mechanical property correlations in molecular crystals. Obviously, you have gone much beyond even crystals. I have seen it. And we are all looking forward to your talk today and your presence here for a few weeks now and several weeks later. And I request my students, young scholars here also, to interact with him whenever he is here, because these kind of interactions are rare. Typically, when scholars interact with the young minds, that generates sparks. It is just one spark that a scholar requires to go further. So here is the spark generator, and you are the spark receivers. Keep the union going. This is very important. I must also tell you that typically in this student age, especially when one is undergraduate, one gets ignited by interesting surprises in the universe, interesting abnormalities sometimes, which must catch your attention. And that is how your scientific journey, your research journey gets made. And these are the type of people who will convey those insights which typically textbooks do not convey. Textbooks are very linear entities. You learn the content, but you do not learn the insights. Insights you can learn only from scholars like him. So therefore, it is a very important occasion for people here to interact with scholars, to get the meaning of whatever they are doing beyond the textbook materials, beyond the research papers even. We will continue this tradition as IOE Chair Professor by bringing such scholars and hoping that these scholars will inspire University of Hyderabad, especially youngsters in the University of Hyderabad, and make this university a pot boiler of some sense. We need to boil here to be able to give light and heat. So thank you very much, sir, for your presence here, and I'm all ears in this seminar. Thank you.
Good afternoon, everybody. I think there are so many good words said about me, sparks and boiling and everything. I hope I live up to at least 10% of those expectations. I will not stand behind the mic. I think it's just will constrain me. I guess all of you can hear me loud and clear. And as a lecturer, I know how to speak loud and clear, so it's okay. First and foremost, thank you very much, sir, for your presence and very kind words. Ashwini and Ghanshyam, thank you for making this possible. My mother is in the audience, so I have to recognize her, all the sacrifices she made. So it's a little emotional. So when you invited me to this university, it's of course in Telugu I always keep saying, of course, Sanskrit Punyam Purushartham, So it was both, I could spend some time with my family, but at the same time be at the university. So this is the reason I am here. I'm very happy to be here. Now, okay, I don't know why this is not coming up. All right, okay, now it's here. So I will take 45 minutes for this talk. So my mainstay right now these days is on 3D printing of metals, which has a very direct industrial connect. But last time I came to chemistry department a few months back, I already talked about it, so I didn't want to bore some of our chemistry colleagues with the same thing. So I'm talking about something else. But this topic is also particularly relevant because as we will travel together in the next 45 minutes, many of the University of Hyderabad graduates and faculty members were associated with this. And as you will also notice, note from the talk, Hyderabad is the pharma capital of India and to some extent the world. And what my talk will be on small molecular crystals and their mechanical properties and how it is related to this. Professor Ghanshyam asked me to introduce my university. I think all of you know where Singapore is. It's at the end of the Malaysian Peninsula. It's a very small city-state. And we are on the westernmost part of the Singapore. Like University of Hyderabad, it's practically a forest that surrounds NTU. In fact, we also have a lot of wild animals like you have, not like you. Not a Freudian slip. But different kinds of things. Maybe not. And we have also iconic buildings, just as you do. And so MTA is a very, NTU is a very young university. And it started as a actually engineering college, and technological institute, became a university about 30 years back. And even 20 years back, when I first went there, it was practical engineering college, only lecturing and whatnot. But it was sort of made phenomenal strides, and this is another topic, how they achieved those. And you can see that it was ranked as the world's best ranked university, which is below the age of 50 for the past many years. And the College of Engineering at the center of it, although it's a technological university, just like MIT, they have humanities, biological sciences, and medical school. MIT doesn't have medical school, thank God for them, and whatnot, business school, etc. So this is a little bit of introduction about NTU. And our school, Mechanical and Aerospace Engineering School, is also one of the things I want to impress upon is the numbers. You see, we take very large number of students. This is something that I think when I look at Indian universities, they don't think scale. This is we take 600, 700 students each year just in one mechanical engineering program, and that is the thing. And the other interesting aspect is there are a lot of corporate labs, a joint interaction between the university faculty and corporate labs, HP, Rolls-Royce, and various other things like that. So now let me get to the topic I wanted to talk about, and this is about structure and mechanical property correlations. And this structure is crystal structure, and molecular crystals. These are not metallic crystals, small molecule crystals. Now, why do we study this? Many of my colleagues joke that I see anything I want to indent or crush or break them, because I'm a mechanical properties Right. But there's, in addition to the scientific interest, there is actually a industrial implication. In pharmaceutical industry, you make active pharmaceutical ingredient crystals most of the time, and so then you mill them, the powder flowability, the tabletability, mechanical stability, there are lots of these kinds of questions coming about. And some of these materials are also being thought about in terms of flexibility and durability in terms of flexible optoelectronic conductors. Now, some years back, somebody wrote this getting physical to fix pharma, and they list a number of things. This is in Nature Chemistry. So, one of the things they say is how do drugs behave as materials that can be practically manufactured. So, the chemical properties of the molecule are paramount. They are the most important ones. But once you identify a molecule, you still need to make it at industrial scale, right, in the manufacturing. And there are lots of issues that come about in that. And in suggesting a number of ways to move forward, they suggest that integrating the material science and engineering approach and the characterization skills that we have is one way to do this. What are material science and engineering skills? So, what do we mean by that? I'll come back to that in a bit. So, in the context of pharmaceutical research, most of the times we take this active pharmaceutical ingredient. For those who are not familiar, if you take a paracetamol tablet, right, it has 125 mg. The tablet itself will be much heavier than that. The 125 mg is the amount of this active pharmaceutical ingredient. And we typically use it in solid form, crystallized, and then you have a formulated product. And formulations is what Hyderabad is very famous for. Okay. So most drug products, you prefer to take them as tablets, right? Liquids, okay, baby is a different thing, but tablets are most easy to administer. You know the exact quantity of the drug that is going in, etc. And the other thing is most of these drug substances are handled as solids, right? And during some point of their production, and there is also patenting issues. It's not just only the molecule that is patented. There is also the product that is patented, and then there is the greening of the patents, etc., etc. It's a multi-billion-dollar industry, and Professor Ashwini Nange is probably far more superior to me than to tell you about these things than I am. Right? So now, the molecule plays an important role in properties, but after you crystallize it, the crystal also makes a very important role in the properties. Right? So what we need to understand is this crystal property correlations to be able to manufacture them in some meaningful way. So I mentioned about already material science and engineering approach, right? That is what is needed to understand this crystal property correlations. Now, so we do this in metals. Actually, metals are the second oldest profession, they say. Metallurgists are the second oldest profession. Don't ask me what is the first one. Go figure. What we do is we look at the microstructure, we polish or we do electron microscopy, whatever, and then we correlate it with mechanical performance. Because a mechanical engineer, when he wants to design an aeroplane, he or she, they will tell you all these parameters, the mechanical performance indicators, and then you go back, you understand, you see how the microstructure determines these properties. So once you understand this connection, you can go back and look at what processing methods will give you desired microstructure. This is what we have been doing, and we have been pushing forward. That's why you have all these fancy cars, flights that you can travel in 20 hours non-stop, etc., are all possible because of this understanding of this connection. So can we extend the same structure property correlations to pharmaceutical solids and other solids is what we wanted to pursue. So this is the kind of microstructures you have in the metals, and we know how they influence mechanical and other properties. But the thing is, when we test mechanical properties of metals, typically we have, you can see the size of the sample. You know, we need kilograms of samples which we can handle, etc. Right? When I go and ask a molecule, Professor Nangia, for example, he can't give me, he can give me kilograms of samples, but the crystal sizes will be still small. So this is where we have been exploiting this nano indentation technique. Basically, we can do mechanical property measurements with very high resolutions of load, displacement in nanometer scales. That's why it's called nano indenter, and even position resolution. So we can locate wherever we want and get local mechanical properties. So this is something that we have been exploiting to use, and I will show you how it is done. So how does this look? So what essentially, all of you must have done a hardness test. We will come back to that when not in a scientific way, but when you test whether rice is cooked or not, you are doing a hardness test. When you pick tomatoes, when you go to market, if you do go to market, you do test, and if it is too soft, you won't pick it up, obviously, because it will get correct, right? So that is the hardness test. Here we are doing it in a scientific manner, very precise way we can measure, and we can get properties like hardness as well as modulus. Okay. What are the advantages? Basically, the specimen preparation is not too complicated. I need a flat surface, well polished. The key advantage is I can get mechanical properties on really tiny volumes of material. Right? So the conventional mechanical test, I need a very, something that I can hold on to. Whereas here, I can really test very, very tiny samples. And that's where we have been essentially able to test very small crystals of organic materials. We can measure localized properties, we can do multiple tests on single specimens, and etc. There are lots of advantages. So these are essentially copper lines on a silicon substrate, and you can see the nano indents that are made, and you can micron mark that is there. So we wrote long ago how that is nano indentation is related to crystal engineering, and this is where University of Hyderabad, because crystal engineering, the whole subject originated on this campus. So this is so how we connect these two. And a lot of these interaction, polymorphism, etc., is something that we can look at as we go along. Now, one of the works we did was look at, because a lot of you are in chemistry people, look at the odd even effects in these carboxylic acids. This is some years back we published with Manish Mishra. So, Bayer actually was the first one to observe that if you take these acids, the carbon atoms in the backbone, number of carbon atoms, and if you plot melting point of the material, if the carbon atoms are odd in even in number, you have a high melting point, and if they are odd, the melting point drops. So it's like a up and down. So this is something organic chemists learn. I understand day in and day out. It's not just only those acids, there are also all these things which exhibit this odd even alteration, fluctuations in melting point. Now, Venkat Talladi, again a University of Hyderabad graduate, for his postdoc, he has basically, this is in JAX, there was a question why these alteration occurs, these are going up and down, right? So, and they did some simulations and computational work, and they say it's not because of the closest pattern. So, now they say that it's because of the strained intermolecular geometry, right, in these odd acids. So, what do we mean by that? So, if you look at the even number ones, C4, C6, C8, they are all essentially flat, right? If on the other hand, if you look at the molecular conformations in the odd ones, they are like this. So the best way to think about it is basically if you are packing a suitcase, right? If you iron all your clothes nicely, you can pack more efficiently etc. And you can fit more things into your suitcase for the same size suitcase. Now, on the other hand, if you didn't iron them, you try to put, of course, it is still packed in, right? You can do all kinds of tricks to pack the same thing in, but it's a strained lattice. You're putting a lot of strain into this. So the minute you apply heat, right, the thing is, this is essentially effectively some TSA agent tries to open the thing, and just boom, it comes out, right? Same way, so when you try to apply heat, it melts faster, the odd ones, because they are not very flat structures. Whereas in the even ones, they are more efficiently packed. It's not, density is not different. Here it is more strained, right? So they basically take much more coaxing in terms of thermal energy. That's why they have higher melting point. Now, why does it happen for elastic modulus? Same thing. If I apply thermal energy or mechanical perturbation, if I can apply stress, these will sort of deform more easily, and that's why I get lower modulus. Anyway, so what I know from our metallurgy context, if I look at elastic modulus and melting point, as long as the crystal structure is the same, so this is for BCC or FCC or HCP, these are a wide variety of metals, their melting point and elastic modulus are correlated. So first thing we said is, if that is the case, I should also have a similar variation as melting point in elastic modulus. So Manish Mishra measured the Young's modulus. So this is the melting point. This is all everybody knows. This is Young's modulus. You see that they are exactly varying in the same way, because they both are governed by the same phenomena, whether it's in metals or in this case. And in fact, if I plot elastic modulus versus melting point, it's even better than what you see in metal, the correlation between these two properties. Okay, so and it is not because of the density variations. They are all, there is a density variation like this, there is no odd even effect. So what we concluded, this is published in JACS a few years back, is that the same features that affect melting point, the same physical principles that govern the melting point also govern the Young's modulus, and that's how we can establish these things. So we can show whatever Thalladi et al. Have hypothesized as to be the true case. Now, okay, I saw a correlation, but how do I sort of tailor Young's modulus if I want to do this? So we had a postdoc called Ghosh, and this is the work he has done for elastic organic crystals. And we took a number of molecules like this and crystallized all of them, and they basically have similar crystal structures, and all of them show very good elastic properties. You can see this, these are thin wires under microscope, they are being deformed, and you can see that they can go to very large elastic strains. And we also can do the same things under nano indenter, now putting it in a 3-point bending configuration and calculate their Young's modulus. Then we look at the molecular packing features, okay, in each of these crystals, I will skip very quickly and tell you what the reason is. So what are the essential structural features that determine, that will give you for an organic crystal, not metallic crystal, organic crystal, very high elastic flexibility? These are basically, you need two features essentially. The first one is you should have a large number of weak intermolecular interactions in all the three orthotropic directions. Okay, they should be dispersive and isotropic. So what happens is, in metals, the bonds get stretched when you apply stress within the elastic regime. In the organic crystals, because the molecules are bound by weak interactions, these interactions break and reform. There is no problem with that. So they act as a buffer for the applied stress, and that's how you get large compliance in the system, good elasticity. But that is not the only condition. If the things slips past each other. If the molecular planes are like tapes, they slip past each other, you get plastic deformation, that's permanent deformation. So you can't have that either. So you have to have this kind of bamboo kind of thing, corrugated packing that you require, so that there is deformation, but it gets locked up after a while, right? So these two features are essential for you to get large elasticity in molecular crystals. This was, it's already 200 times cited, so a lot of people actually went and confirmed this in a number of molecular crystals afterwards. So, so this actually works. Now, this Mangalampalli Kiran, not Mangalampalli Balamurali Krishna, but quite close to the place, is Professor Ghanshyam's student who got PhD at University of Hyderabad. He came to IASc as a Kothari fellow. So, and Malla Reddy again is a PhD from University of Hyderabad chemistry department. He's a professor at IISER now. So basically we started our first work on saccharin crystals. We took, because these crystals are something we can grow easily and get access to, and we indented on two faces of the crystals, 100 and 011, and we get differences in responses. Let me illustrate. So if you look at 011, right, when I poke the crystal on the 011 face, the response is very smooth, right? The indenter penetrates very smoothly, and then I get the properties. But when I poke the same crystal on 100 face, I see a lot of these discrete steps. So why is it happening? Basically, if you look at the crystal structure, that is the indentation direction. So it is like a pack of cards, right? If you take a pack of, especially fresh pack of cards, if you shuffle this way, it's very easy. But if you try to apply load this way, at one point it has to yield, and but it will be jerky, right? So that is what is happening when you indent along this direction. But when you indent on 011 plane, these basically there are slip planes that they can slide relatively smoothly. That's why this is happening. This is the kind of structure property correlations we can do for these materials. And then one other thing that he observed is these pop-ins, what we call discrete displacement bursts or pop-ins. They are multiples of 18 nanometers, and that there is a mechanics reason for it. We can actually explain this in purely using mechanics, indentation mechanics principles, why that is happening, and that we did that. And I won't go into this in detail here. So after the foray into saccharin, that's only the beginning. We started looking at polymorphic forms of molecular crystals. So for those who are not aware, what are polymorphs? So here is the definition. A polymorph is a solid crystalline phase of a given compound, which will have at least two different crystal, which can occur in two different crystal structures, right? So carbon can have many allotropes, and so in molecular crystals you have a number of different ways. Now polymorphs are very, very important in pharma industry. There are a lot of complications to that, and I will illustrate a few examples to you as we go along. So when you have polymorphic crystals, we saw this slide before, but now you have two different crystalline forms. The way they respond, the way they behave as drugs will be very different. The efficacy could be very different. Professor Nangia has done on curcumin. The curcumin is the molecule that is in our pasupu, turmeric. So that is the one which gives the thing. But curcumin has this problem, for example, that it's if you why do we have to use turmeric in our food? Instead, we can make tablets like vitamin tablets. But the problem is biosolubility is very poor. So if you take it as a tablet, it won't quite work. You have to put a lot of pasupu in your dals and sambars, and that is the only way it will work. So, so polymorphic forms are very important, and one of the things we looked at is aspirin first. Aspirin is, so 40,000 tons of aspirin is consumed worldwide, so now there was, everybody thought there was only one form of aspirin. And Peddi Vishweshwar, again, a University of Hyderabad graduate, so you see why I chose this topic now. But after this was his postdoc with work with Michael Jawaratko. So many people started questioning whether there is a form 2 of aspirin, right? There is the title itself can tell you it's elusive form 2 of aspirin, and then there is also the headaches illustrated by aspirin. So the reason it was visible, not visible, sort of, it was playing at that time, whether, many people say there is no aspirin 2. The reason that it was the case is because people rely for solving these structures on Xray diffraction, right? You essentially start a solid state chemistry department anywhere. Okay, first thing you buy is Xray diffractometer and single crystal Xray diffractometer if possible, right? So the problem is Xray diffraction is not really giving results. There is a because the diffraction patterns often are in weighted overlay of form 1 and 2, and form 1 and 2 are as such sort of fairly overlapped, okay? Right? So, and if you take one of these crystals, form 2 crystals, the domains of form 1 could be there, etc. Now, we thought we will try to look at this problem from with using nano indentation, right? So, so let me give you a little bit detail. This is the structure of form 1. The color is red. So this is the crystal structure, right? You arrange that. Now, if I, for example, shear the middle layer like that, and that's how I get form 2. So this is the form 2. So the unit cell dimensions A and C are the same. Form 1 and 2 are related through this shear, right? And that's, I can express it this way, with this transformation matrix, how form 1 and 2 are related, okay? So if I take the blue, that is form 2, and I apply shear, like a cardboard box that is slightly off, and I can get form 1, right? So we did indentation on this. This was published in 2011, more than a decade back. And what happens is, if I indent on the same faces, 100, form 2 gives me much softer response, right? Same crystal, slight difference in structural packing, and it gives me huge difference in response. The reason it happens is, when I indent on this face, form 2 goes into form 1, okay? And there is actually, I won't bother you with all the details. Please read the paper. There are a lot of these things. Why that happens is we actually pinpoint exactly. Now, one of the difficulties we had is the person who grew these crystals for us is somebody named Andrew Bond, and he sent it to us, and we struggled with experimental results for a long time. Same as Xray diffraction. We were getting something sometime and something else sometime. Eventually, Kiran figured out that when he takes a crystal, this is the actual image of the crystals. So if you indent in some domains, you get one response. Some other domains, you get a different response, right? So because there is this intergrowth polymorphism, so you think it's one crystal, right? It's like Ardhanarishwara, maybe some way. The thing is, you think it's one crystal, but it's one domain, it's form 1, and one domain, it's form 2. So when you do Xray diffraction, you get a mixed signal of all this, because even if you take microfocus Xray. With nano indentation, because we are poking locally, you're getting different responses, okay? And in fact, when we published this, we submitted it to Nature Chemistry. They won't, because this was a debated topic, they won't publish it, but subsequently they wrote a viewpoint saying that, we solved the aspirin's headache. So anyway, so then we went further ahead and said, okay, this was sort of a serendipitous experimental result. We weren't expecting it, we weren't even looking at the direction. Eventually it clicked in our head, and then we got the answer. So we said, look, let's design a case. So we took another molecular solid. This is felidipine, again an important API. So It also has 2 different crystal structures. In form 2, there are 2 different types of cells are possible, cell A and cell B. This Xray diffraction is combination of both. So now let me just tell you this. So if you were to look from the top, if you were to indent from the top, right, these crystals, the indenter will not be able to recognize which is what, because the structural difference is different from this direction, right? So if I poke it from the top, I should get some sort of a distributed response. But if I poke it from this side, if I am indenting on a region which is cell A, I will get one response. If I am indenting with a region which has a cell B structure, I will get a different response. So this is what we hypothesized, and we went ahead and looked at it. So this looks like a cake. There is a purpose I put this here. Now, so if you look at, right, this is a layered cake, strawberry shortcake anyway. So if you were to indent from the top, you will get only one response. It would not know that there is a layers of the material inside, right? But if I were to indent from the side, if I just take my finger and poke, I get a slightly harder response, and then here I get a softer response. That's what we hypothesized, and we looked at it. So when I indent from the top, there is some stochasticity, but that is because we are measuring local properties, but all the curves are same. But when I indent from the side, I do get, these are the responses. You can see they are already segregated into 2, right? So I get very distinct responses, and there are some in between because we maybe have at the interface of those. But so this tells me that so Xray diffraction would be very, very difficult to resolve, right? What with indenter, because this is a nano indenter, I can do it with very fine spatial resolution. I can actually go and look at it. I can actually look at the microstructure of the material. So my young colleague Jay does this in your school. He is looking at steels, which have martensites and austenites. So he goes with nano indenter and probes, maps the mechanical properties. So if you have an intergrowth polymorphism, you have essentially a microstructure to the material, right? Even if it is a single crystal, there are domains of form 1 and form 2 and whatever form. You can actually do this, right, with the nano indentation. So, well, let me again connect with you. So I think the nano indentation guys would know. Right now, when you see these 2 bunches of bananas, if I ask you which one look ripe, you will say the right ones look ripe, right? It's no brainer, no difficulty. But if I blindfold you and bring these 2 bunches of bananas, will you be able to tell me which one is ripe? It can be bananas or something else, right? You will still be able to by just gently pressing them, by measuring their hardness, right? What we are doing is not so different from that. I keep telling you, do hardness test all the time in your real life, and this is what basically it's $500,000 expensive machine at very high resolution, but otherwise it's the same thing that we translate it to very thing. So because now I can take a crystal that seemingly, even if I take micro focus X-ray diffractometer, seemingly one crystal structure, I can actually, if there is a microstructure, I can poke on it and get if there are domains of different polymorphs in it. So that is the idea. Now, so we looked at elastic modulus and polymorphism. Switch gears a little bit and look at the plasticity. I think I may have another 10 minutes. So with Malla and we did this work, and Kiran again. Mechanochromic luminescence. So mechanochromism is basically if you apply stress, there is a change in the color, and that is what we looked at. So there are some materials like this difluoroboron, benzoin. So you can see my chemistry is very poor. There is reversible mechanochromic luminescence. So MCl. Okay. So you take a thin film of this material, you apply, and you take a cotton swab and write on that. That's mechanical stress, right? It changes color, right? And then if you heat it up, it will go back to its original color. So this is what reversibility is. Okay. Now there were a lot of questions as to why this happens. What's the mechanism? Okay. Why only some fluoropores exhibit this? Why others don't exhibit this? Okay. So we took the same material, and so if you look at it has again two crystalline forms. Okay. Two different crystal structures. Form 1 will be in green shape. Form 2 will be in cyan, right? So form 1 is very brittle. These crystals are, you can see they are, if you apply stress, they break like chalk pieces. They are stiff and brittle. Form 2 is very soft and compliant. It's the same molecule, but the way it crystallizes changes its properties dramatically, right? And its mechanochromic luminescence is also very different. So for example, if I take the green form, its reversibility is very poor. Okay, even after many minutes, it still remains. On the other hand, if I take the cyan form, it just recovers very fast, even at its prominent recovery. So these two exhibit very distinct responses in terms of their recovery characteristics. So we did indentation, and you can see that the results are summarized here. So this material is stiffer, harder, almost twice as that of the compliant and soft one. So you can say, look, this I can also do just simply bending and whatnot, but nano indentation gives you actually precise data. Okay. Now, why are the mechanical properties different? So that is where you look into the structure of the material. So if you look at the structure here, right, in the green form, there is no way for the molecular planes to slide, right? It's very interlocked structure. So even if I apply stress, the stress has to be accommodated, right, by the crystal. In metals, these things happen through dislocation motion, as we all know, but here there is no mechanism for that. Whereas if I look, by the way, it's the same molecule. There is no difference in molecule. It's a different crystal structure now. So you see here, there are these dashed lines along which they can slide. Okay. When they slide, what happens is, if for example, this molecule, this layer slides by that much distance, there will be again a registry, right? It essentially goes through an activation energy barrier and comes down. So because of that, there are these slip planes, the molecular planes which can slide past each other relatively easily, the shear past or slide past. This one exhibits much better reversible mechanochromic luminescence. That is the underlying pinpoint. So this is we argue and tell a lot more details about this in our paper. Okay. So whether you have slip planes or not makes a lot of difference, and you can now start looking at crystal structures and see whether those kinds of signatures are there or not. Now, so the other thing is in the polymorph forms, we can also look at the stability. Okay. So this is actually the work done with Palas. Shanti is Professor Nangia's student. The work, this paper is from University of Hyderabad. So this is curcumin, the one in turmeric, right? This is the molecule that gives you all these fantastic properties about for curcumin, pasupu, haldi, if you want to know in Hindi. There are 3 different forms, and the stability is, of course, form 1 is the most stable, and form 3 is the least one. We also did looked at another drug molecule, that is sulfathiazole, and then again it's the order is 2431, and so we looked at the stability order and how what is their solubility. So hardness versus solubility, and you will see that more stable it is, higher the hardness, and least the solubility is less, because solubility is increasing. So the softer is more soluble. Okay. Maybe intuitively, I was arguing with my collaborator at that time, this is intuitively makes sense to me, but scientifically these are correlations that you actually have to argue and say that this is the case. Now, so softer materials give you more solubility, but from a manufacturing point of view, softer materials are not good, because in Ready Labs or other pharma manufacturing, they grow these crystals in large vats, and then they do subject them to something called micronization. They basically grind these crystals into fine things, because you need finer crystals, because you want 125 milligrams, you should have exactly that kind of crystal. So, okay, how do you tailor hardness? This we showed with omeprazole. So basically it's a tautomer. So by changing the content of the tautomer, you can actually vary the hardness. So if I look at the form 1, I hopefully again you see that is the softest, and I have all these slip planes, so it easily slides past each other, and then that's why you get low hardness. But when I go to other forms, they are sort of interlocking, increasing interlocking, and as a result hardness keeps going up. So this is a schematic illustration. Form 1 is like this, and form 2 has these extra things. If you go back and look at the actual crystal structures, you see these red dots. They can sort of start more and more in number, and as a result you have this. So this paper is, my metallurgy friends will like it. It's called solid solution hardening. So you play around with the tautomer content as a percentage, and you can actually change the hardness. So you can actually do these kinds of tricks, which metallurgists we know for centuries or maybe decades at least, and you can apply these to change the hardness of a molecular solid. So we learn these tricks can be applied to molecular solids as well. And in fact, you can think in terms of either forming co-crystals or salts. This is on voriconazole, again another API, and so you can essentially play around with E and H variation. How much time? Who is my chair? So, all right. So this is the thing, and then I will last two topics. This will not take time. I'll just so more recently we have been looking at synthons. So again, this concept of synthons as the sort of building blocks of crystal structures, the crystal engineering concept has started here. So this is the work done with Malla Reddy. So we took this particular diimide derivatives with methyl, ethyl, and N-propyl alkyl groups, and you see the base molecule base is same, but these alkyl chain lengths are different, longer, and as a result the crystal structures are different, and because the crystal packing is different, this material is very soft. You can bend it, you can see. And on the other hand, if you come to this, you can't bend it at all. It's very brittle. It breaks like chalk piece, right? And this one is highly flexible. And you can see there is already, I talked to you about what are the kinds of things that are required for getting high elastic modulus, right? You know, so that is there here, right? And we can again do nano indentation and connect it with the crystal structures. And in this case, we also do not only just indentation like this, we can also bend it, use the same nano indenter, because these are really tiny crystals. If you go to a regular mechanical engineer, they'll say, look, I can't handle this. This is so tiny, you can't even see them. And this is where we use our expertise to mechanically test and derive these things. Okay. Finally, this is not something that an area that really I have left. I'm still working on it, although as I said, we are doing a lot of work on additive manufacturing. Recently, we have a Nature Communication paper on 1D coordination polymer, and again, this synthon concept, copper, and these synthons are there in this, and basically here, I hope you can see this is when you bend, it's like mica. If you bend it, it's essentially can accommodate a lot of deformation, and so it's a plastically bendable 1D coordination polymer. And we did a lot of Xray diffraction and other things. So in these, let me just, this is what you need to focus on, right? So what our Raman spectroscopy and DFT, first principle calculation, show that these interactions can actually stretch or do this to accommodate the applied stress. And that's how you get the plastic bendability. So you can take these materials, and which previously were applicability in terms of mechanical properties were very limited. You can use them for expand their application potential with these kinds of things. So this is the mechanism. You see that there is a delamination that can occur because of the kinds of bonds that easily can be broken. Let me summarize. It's already quite well late in the evening, and I know some of our colleagues are missing their walking schedules, and they are looking with a very evil eye towards me. So not quite. All right. So chemistry. Before I start interacting with them, I only knew about 3 bonds. I think Vice Chancellor talked about being open to opportunities. So I didn't even know what intermolecular interactions were. I know about weak bonds, van der Waals forces, and whatnot. But what happened is I was interested, curious. I wanted to learn. And one of the things that is if I work in an area for 10 years, I get bored. I want to, first thing being an academic is you have to be always satiated with respect to knowledge that you gain. There is no end. So somebody came along, we started interacting, and it was very rich. So the fact that I could stand before you and give a talk about things like this, which would be impossible, would have been impossible 15 years back, shows that that once you get out of your comfort zone in terms of what you want to learn. Because when you start working with somebody who is in a different field, the frequencies don't match. Their language is very different from your language, the technical language, not the lingua franca. And so you need to learn a lot, but that's fun. That's the reason. So it's very important, especially for younger colleagues, is that you got to get out of your comfort zones. This is something that happens very often, especially in Indian context. You work for a PhD thesis in a certain field, you postdoc, and afterwards it's very comfortable. You know the language, but you continue in the same well-trodden path. But sometimes you have to take side routes and see what is there, and sometimes you may find very interesting stuff. And that is this journey has, at least in terms of molecular crystals, has shown us. One other interesting fact is I never actually sought funding for this work. I could have got, no problem, absolutely easy, no worries about it. I never got rejected for funding. I always had a lot of money, research grants, not personal money, don't get wrong. So the thing is, that is, but it was more of, for fun, we wanted to learn more, what we can do, keep pushing. And this now is, I'm pleased to tell you that it's very dominant hot areas in chemistry, in solid state chemistry, I can tell you this. So, and there are lots of interesting stuff. We literally and figuratively only scratch the surface. So there is a lot of opportunities for this area to grow further. And so I hope I gave you some glimpse of the kind of work we have done, and maybe there is some excitement. Not quite lit the fire, as Professor Rao asked me to, but took you there. Thank you very much. Yeah, sure, as long as the...
Yeah, please, Samar.
It's just query. These kind of properties have been checked for graphite crystals. Any report is there?
Graphite, yeah, must be. I haven't done it, but I'm sure graphite is,
because it has also many crystal.
Yeah.
Another things, can you tell little more technicality of the indentation? You gave fantastic example of cake. One can feel by finger, but actually on crystal, what to do? I don't. So, I do not know actually.
No, it's fine. Yeah. So what we do is okay. Let me go back and so hardness tests are done in all manufacturing industries. When you go to a steel manufacturer or any manufacturer, they do heat treatment and then generally test hardness. What do they do is they take a flat surface and take something which is an indenter, which is the tip is typically diamond or tungsten carbide, much harder, and you poke it. You apply 10 kilogram force, you poke it, remove it, and then what you measure the imprint made. Okay, so the imprint divided by the force applied gives you the hardness. Okay, so in the nano indentation, which we also call instrumented indentation, what we do is as we poke into the material, we basically measure the force as a function of depth of penetration, both while loading and unloading. Okay, and this we do at the instruments do rather with very high resolutions, very high force resolution, displacement resolution. The requirement is, even although we say that it's a nano indentation, I need still a crystal that is a couple of microns thick. Yeah, so we need to hold it also firmly because I'm measuring displacements which are very, very, a few nanometers. So if the thing wiggles, then I get a spurious result. So
how is the crystal held in place?
We either glue it. There are techniques to do it. We can also hold it other ways. Yeah.
Glue it
on some substrate that So, and that's why a lot of times we do on the major face, because that is the one which you can Yes.
So thank you, Professor Ramamurty, for a wonderful lecture.
Thank you.
And it's very exciting. I have a very simple question. So molecular crystals are all about the weak forces, and there are several types of them, starting from van der Waals to dispersion to dipole, pi, and so on. So when you do that, this just to know information, nothing more than that. When you do the DFT calculations, I'm sure one has applied the dispersion force corrections to do these things. Is there some insight into what actually is the proportion of the various types of weak forces which are actually controlling these things?
Simple questions are like googlies, right? They look like you can drive them to 6. No, but in the case of aspirin, I remember, this calculations to show that aspirin 2 is energetically not favorable. There were, because in the DFT calculations, the many body interactions and especially the weak interactions are very difficult to capture.
So the Grimace functionals are there.
So that was the problem, and there was a PRL that was published, quantum of solace. So given that one of my collaborators is Bond, not James but Andrew, and there is a movie, James Bond movie, Quantum of Solace or Quantum Solace.
Yes.
So actually that is what I was. So but the problem there, I do remember, is that in these many body interactions is a very difficult proposition to capture, especially for weak interactions. So, and that's where I think in terms of the predictive capability of the crystal structures, in terms of this is a bit of a challenge still, as far as I understand. Maybe Ashwini knows a little more about this.
one wall. Yeah, yes. We'll continue that. Thank you. Sure. Thank you very much.
Thank you. Yes, Koti.
Yeah, fascinating lecture, sir.
Thank you.
First thing is that what about the density of these materials? Are they 100% dense?
They are crystals. They are single crystals. They are not polycrystalline metals that you think of. So the crystal density is what the density is. So there are the dislocations, etc. Still a question. Could there be twinning? That's a different question. But in terms of what metals we think of, porosity, no. The porosity, there is a structural porosity. If you take metal organic frameworks, there are open holes, but that's the intrinsic structural feature, not a porosity that you think of. Yeah.
So in such a case, have you seen any inelastic behavior in this?
Oh, there will be plenty of inelastic behavior. Absolutely. Yeah. Inelastic rate dependency will be there significantly. We looked at also those aspects. Yeah.
And how did the load dependent hardness go in these crystals? Have you got a chance to look at that?
We no, the indentation size effect is what you are referring to. No, we didn't do that. It's these are tiny crystals. We didn't really bother that. Yeah, you know that in metals we look at indentation size effect all the time, but not in this case. Yeah.
Okay, and the turmeric and all, they were in powders. What you showed the images were in the powders.
Those powders are just illustrations. We didn't take powders. We do single crystals. So somebody has to grow these crystals for us.
Okay.
Yeah, they are. Yeah, okay. That's actually I think his lab's image. So you know that's Palash's. Yeah.
Yes, they look like powder.
Yeah.
Yeah, please.
Professor Ramamurty, fantastic talk.
Thank you very much.
I'm not an expert in this nano indentation. Question might hurt very stupid, but
no, it's all right.
It keeps coming to my mind whenever I see such load displacement data, and you are deriving a lot of mechanical properties from that raw data. Am I right? So my question is, when you are taking some material, putting some A on it, putting some load, and the response you are getting from this material, you are using that data to derive your properties. My question is, does it not depend on the support?
Of course.
See, for example, See, for example, I have a very solid support versus I have cotton.
Yeah.
I have put my material and putting the load, right? So the normal reaction.
Yes, I know what you are.
So then the properties that you are deriving, how can they be solely representative of the material, not the load, not the support?
No, machine compliance we have to take. We have to fix it properly. This is so we do that obviously. So so even if why nano indentation, if you do mechanical macroscopic test, the machine compliance is something that you need to worry. So nano indentation, we know we calibrate. And we also make very, this is where our, experimental.
So that means the support part is taken care of.
Of course.
Otherwise, it will not have any.
So, of course, yeah.
Thank you.
Yeah.
Hi, thank you for a very informative talk. I wanted to know whether, based on your research work on molecular crystals, do you find any correlation between the hardness or the softness of these crystals based on the bioavailable polymorph? Like, is there any trend like
bioavailable
polymorph or API, which I was talking about? So if that API is the bioavailable one, can we say that most often you see them as hard crystals or soft? Because many times the bioavailable APIs are metastable, right? So that correlates with what you were saying, like the soft materials that dissolve very quickly. So is there a trend between the softness of a crystal which is bioavailable?
So we don't have a direct evidence. So what we could establish is hardness and there is a correlation, but it's not a linear one. You see that there is it's but correlated data. Beyond that, no, we can't say anything. But it's from the two sets of data. It's not exhaustive even. Generally, softer looks more soluble. That's the only thing I could say.
I have one quick question. Is the aspect ratio of the molecule and the force you measure or slip planes you measure using nano indentation, have you studied those correlations?
No, it's only, the molecule length is, we look at molecules crystallize, right? They are organized into crystal, and how they organize into crystal and how the properties are related. So if they, for example, if it can be long, but they can organize in a complicated manner, then you get a brittle thing. If they are organizing in a layered manner, you may get a ductile response. So it's the organization that matters than what is the length of the molecule. You can take Vanaras and beat Sri Lanka, right? Ravana. So it doesn't. It is as long as you have the Vanaras organized. Well, I don't know whether it's off tangent, but just should give you. So maybe that is the way to say.
So can I ask a couple of curiosity questions?
Sure, sir.
Does the process of micro indentation itself change the properties there?
Yes. Actually, I missed I think I didn't show you. So indentation, when you do that, you're applying stress,
Yes.
right? So there could be stress-induced transformations. So in the aspirin case, there was actually a stress-induced transformation from form 2 to form 1. So what we did was, to confirm this, we took the pestle and mortar. We took aspirin form 2 crystals, we ground them, and then lo and behold, they become form 1. So, there is this huge opportunity we believe we haven't explored. There is a huge field called mechanochemistry. If you basically look at our traditional medicine processes, they take a bunch of various herbs and they grind them together, and then some chemical reactions must be happening. So that happens under the stress. So now you have a tool to quantify them. And that's the thing, what is happening. Of course, again, I want to emphasize that we are only literally scratching the surface. Yeah. So there will be stress-induced transformations in form aspirin that happens quite clearly, and there could be happening in other solids also. So I think Manju talked about metastability. So if you have metastable situations, you can stresses can actually push them to more stable configurations.
About the polymorphs, because it's coming from the same chemistry essentially. The
Yeah.
core chemistry is the same.
Yeah.
So are there these initial conditions that dictate the nucleation and then they propagates? How does it happen at a bulk level? Who initiates this?
Ashwini, it's a crystallization conditions. So what? See, typically the energy states of the polymorphs are not necessarily the same. I'm looking at Ashwini because he's probably better equipped to answer your question.
Is this a nucleation phenomenon?
Yes, sir. It's a nucleation phenomenon. It must be nucleation.
Yeah. That's right. That's right. Right.
Yeah, it's nuclear. Yeah, it must be. In metals, that's the case. But energetically, not all of them are same energy states. So
there may be minor differences.
They are trapped. Yeah. So in glass, in an energy landscape, they are trapped in slightly higher landscapes than lower.
Earlier it was an enigma. Now we understand more about it to be able to direct it towards form A or form B. More predictable. I think there were several hands here and there.
Sir, generally when we do nano indentation for metallic materials, we see the surface finish, how best it will be for performing nano indentation.
Yeah.
How it is about the molecular crystals?
Yeah. So certain expertise is essential. For example, Kiran got after a long time. See, by the way, professors sit in their rooms and chat with other colleagues and give talks like this. The postdocs and students who do the work, and hopefully I acknowledge them enough. So Kiran figured out how to do it. What he will do with our case is basically scan the whole thing and look at flat regions, because these are single crystals. Metals we know polishing, and we have all the techniques that are available to us. But these cases you need to really look for a flat region to test it. So that we have with the high citron triboindent, we can essentially scan. We can find where flat regions are. Yeah.
And how is the handling of the molecular crystals to the nano indentation system? As we use tweezers or something, there will be damage to the crystals, and we see most of the area with a damaged surface. How to locate the proper, how to handle the crystals?
That is where the trick is. Some people have good hands and it's skill. Yeah, it's very much skill. You have to really know how to do this. And by the way, when this is always a scary thing. Are you getting? Somebody pointed out. He left, I guess. Yeah, so you're getting spurious results because of the thing. So. You have to really have skillful hands and do this. That's true for any experimental work, and this is delicate stuff. Yeah.
The Heisenberg limit of any experiment. Don't disturb the system while you are.
Yeah. Yes.
Yes, sir. It was a very excellent talk, actually.
Thank you.
So I have a very simple question. Like
everybody says simple question, and it's Abdul Qadir's or what with Googlies. Yes. Okay.
Yeah. Once you perform this experiment on a crystal, perfect crystal, we apply some kind of force and we deform the crystal basically. So essentially the crystallinity of the material is lost.
No, not necessarily. Crystallinity is not lost.
Okay.
No, it's still crystal. It's just deformed.
Deformed.
Yeah.
Okay.
No. Crystal. There are metal organic frameworks which go through amorphization.
Okay.
So when you say crystallinity is lost, you mean it must have amorphized, right?
Okay.
No, that doesn't happen.
So it's not amorphous.
The crystals. So there are others. Somebody else did NMR studies around these things. No, they don't really. There is some defects that are created in the lattice,
okay.
But it's not crystallinity lost. Go ahead. Yeah.
Okay. So my question was like, after the performance of the experiment, how do we find the structure of the crystal? Because
we don't. We
do we rely on some theoretical methods or some other experiment?
No, we don't have the tools to really go back and look at. We can actually image the indents. We do that, but no, in terms of crystallinity is lost or whatever. Or what is the crystal structure if there is no. So we do indirect experiments as I illustrated with aspirin, mortar and pestle to get confirmations.
Okay.
Yeah.
Increasing limits of diffraction, I think.
Maybe one day one can.
Okay. Redo the structure after.
Yeah. That will be nice. Actually, See, in metals context, we know what facilitates. See, you take a piece of metal, right? You can bend it, and civilizational progress has happened because. As progressively we know how to do metalworking, the copper age, bronze age, and to iron age. That's because harder and harder materials, but you can also do lots of different things. We exactly know what happens. So here, what is we know they deform. We can connect this with these crystal structures, but what sliding of the molecular planes. But precisely yet, I don't know. Okay. What are the carriers of plasticity in molecular crystals? I still don't know. There is a lot of things, maybe modelers like you can shed light on.
Sure, okay.
Yeah, it's related to the question Professor asked and also JJ was asking. When you try to intend some changes might happen in the molecular level, but we can probe it using spectroscopy, right? No, because these days microspectroscopies are there.
Yeah. But the thing is, do remember these are really still tiny, very tiny volumes. Okay. The indents actually, by the way, they are not visible with naked eye. Even our optical microscope, we have to use the same nano. If you take this crystal out and put it in a SEM, coating and whatnot, you can't see it. So basically, it's in.
I mean, laser-based Raman spectroscopy can do directly.
Spectra, people have done Raman actually. Yeah, the high citron company guys have done Raman, and they looked at one of the materials. I don't remember which one. Yeah, crystal.
Let me ask my question.
Sure.
The question is. So when you try to do indentation, how you rule out the possible any force applied to any materials having some modulus, when you poke it with the indenter, how you will rule out the possibilities of nano cracks happening because of the tip sharpness, and then how you can eliminate this? I mean, this is some kind of
cracking. No, we can look for cracking. And no, the cracking doesn't happen. So, by the way, my actual bread and butter is breaking materials. I do fracture and fatigue as such. That's my thesis, and that's what actually I do. So, for crack to form in a material, even if the most brittle material, you take a window glass, that's the most brittle, 0.5 ampere root meter fracture toughness. You need a certain amount of energy, a critical energy density that is required to drive the crack. So. And these are generally plastic materials, and the energy that we put in, through the nano indentation is just in terms of quantity is abysmally low. So it will never drive it to cracking. So if we do micro indentation, maybe then we can have cracking, but we can image those. Nano indentation, even if there is enough absorption mechanisms, even the most brittle materials you won't get cracked, and these are not definitely there.
Thank you.
Well,
one last.
Okay, sure. Yeah.
So
always
you talk about
student
crystals.
is a special status. Yeah, where is the question from?
Yeah, you talk about crystals, but during nano indentation, do you feel that there is some indentation creep?
Creep will occur, and especially these cases because the weak interactions can with time break and reform. So there will be a rate dependency and time dependency as such. So we have looked at some rate dependency, but not really the creep effects. Yeah. I think people have started looking at it. There is I think yesterday or today I saw a paper on looking at creep characteristics. Yeah.
Shall we say last and then we try to wind up?
Yeah. Sir, towards the end of your lecture, you said Raman, you did some calculations. I mean,
no, I didn't do it.
Raman calculations were performed to look at the elastic behavior or mechanical compliance of the molecule. So, how are these changes, like theoretically predicting the Raman bond stretchings, is giving insights into the molecular level changes that are actually impacting the mechanical properties?
It's I think DFT calculations look at density of states and things like that. So basically, in explaining, you have to do all the various different experimental techniques, right? So Raman gives the shifts that are associated with the stretching of these copper-copper bonds and or interactions. So and then DFT calculations also confirm that.
Sir, but if you look at the actual actual mechanism of bending, like the atom movements are so tiny that how do you give that tiny movements in the theoretical calculations you are performing?
That's what I think. If I go back to that slide, I think they have those bond extensions. You see here the lengths are the copper 2.983 angstroms to 3.034 and 3.211. Yeah. So there are those stretches. It's very tiny, but it's this reasonable strain.
But beyond the standard deviation.
Yeah, these are reasonable strain values that happen. And that's so the adaptability of that copper-copper interaction is what gives this particular coordination polymer this plastic bendability. That's the argument.
So one more, like so probably last. Like if you when you look at the NDI like naphthalene diimide case you are showing the plastic behavior and elastic behavior with Malasa.
Yeah.
So there, if you look at the crystal packing between the plastically bending molecule and the elastically bending molecule, there is not great difference in the crystal packing. Even the stretch, like the slip lengths you show. So recently there is a debate that a lot of molecules with slip lengths also exhibit elastic
this
behavior.
is a Clegg, yeah. So I know.
And not in particular to Clegg, but there are several other molecules which we have also seen where they have slip lengths, but still they behave elastic.
So yeah, this is
so
where
my question here is: does aspect ratio has a role to play when we are going from elastic regime to plastic regime?
So subtle differences could have a profound impact in terms of the mechanical response that we know in the context of metals. So I would expect molecular crystals to be no different. Again, can you specifically? So in terms of molecular, I strongly believe it's not the molecule that matters, but it's how they organize matters. And subtle differences, you say, naphthalene case, there are only subtle differences, could be humongous things. See, one of the problems, and Bill Clegg and I had a Twitter feud a little bit, and then they gave up. See, I come from mechanical engineering or mechanical properties of material. So, elastic flexibility. Flexible is actually only elastic for me. There is no plastic flexibility. So, Clegg says plastic flexibility, and I told him, Bhaiya, this is not your. See, this is why when pronouncing chemistry stuff, I'm a little edgy because that's not really my cup of tea. Mechanical properties come, until tomorrow morning, I can argue with you. So that is where I think when you work in interdisciplinary, what happens is you got to be very precise in language. So that seems to be eluding some of the chemists who are working in these domains. That's why it's very important that you link up with. There are people here, who do nano indentation in day in and day out, and then the terminology will be right. Because whether it's a chemistry person or a mechanical metallurgist or a biologist, the language, the technical preciseness has to be there. It can't be imprecise.
I hate to interrupt this very lively debate. We could go on. There is tea, coffee, beverages outside. I think we can enjoy to continue this discussion. It's almost been at the level of a Faraday discussion, the question and answers. So a big round of applause for Professor Ramamurty. He has truly shown us what interdisciplinary research is all about, and I'm sure we will all push the boundaries beyond the comfort zone after his lecture. Thank you very much again.
Please wait for a couple of minutes, please. Now we'll request our Vice Chancellor, sir, to felicitate the distinguished speaker for the day. Thank you, sirs. Before we break for tea, I would request Professor Chandrasekhar to propose the vote of thanks. I think two. Yeah, please.
Okay, so a proper vote of thanks. Dear Honorable Vice Chancellor, deans from various schools and colleagues from various schools, and my dear chemistry colleagues and students, thanks for coming here to listen to Professor Ramamurty's distinguished lecture. And just let me tell you what I have in my mind. It's indeed this topic of this lecture is very much fitting to our celebrating, mood of eminence, which is focusing on the interdisciplinary clusters, research, all those things. So it's very much fitting. And also, as Professor Ramamurty was mentioning about the importance of interdisciplinary research, just a little bit of, key kind of history, I can say. So this research on this crystal mechanical property was started by Professor Desiraju, and accidentally he discussed with Professor Bhatnagar. He was associated with the School of Physics that time. So that interaction between School of Chemistry and Physics led to a very interesting output for the first time that people could correlate how different molecular crystals can respond when you apply a mechanical force. And that happened, the publication happened in 2005. And after that, this field is really big. Many people are working in this field. And we are, as Indian, we have to be really proud that this originated from School of Chemistry. Okay? And apart from this, to conclude, what I would say is, we need more talks between different departments and schools, and more such collaborations, and also more such eminent interdisciplinary talks, such as this one. Thank you all.